students, a very warm welcome to my channel Ritugat Maths Classes. Today we are going to take up some extra questions of chapter 5 differentiation for class 12th. Some of these questions have already appeared in previous year's board exams and some are higher order thinking skills questions. So let's start with the very first question. Find dy by dx if sin x is equal to 2t upon 1 plus t square and tan y is equal to 2t upon 1 minus t square. It is a parametric form given to us. X and y are taking the support of the parameter t. So let's start with the solution. Sin x is equal to 2t upon 1 plus t square and tan y is equal to 2t upon 1 minus t square. So if I apply sine inverse on both sides, LHS becomes sine inverse of sine, that becomes identity, and we are left with x. And RHS becomes sine inverse 2t upon 1 plus t square. This is nothing else but the formula of 2 times tan inverse t as given in the second chapter, inverse trigonometric functions. On this side, applying tan inverse on both sides, tan inverse of tan becomes identity, and we are left with y is equal to tan inverse 2t upon 1 minus t square, which is again the formula of 2 times tan inverse t. So from here we can easily see that x is equal to y, that is y is equal to x. If y is equal to x, then differentiating, we have got already y is equal to x, differentiating both sides with respect to x. Both sides with respect to x, we get dy by dx, derivative of y with respect to x, is equal to dx by dx, that is 1. So this is the value of dy by ds as asked in the question. Now we are going to take up second question. Differentiate sine inverse 1 by whole under root x plus 1 with respect to x. So let's label our function first of all. Y is equal to sine inverse 1 upon root x plus 1. If you want, you can differentiate it directly also with the help of the derivative of sine inverse theta. But I would like to put some substitution to simplify the function. Now the substitution should be like this. If the outer function is sine inverse, I should get internal function as sine. So I have taken x is equal to cot square theta. Let's substitute it over here. 1 by under the root cot square theta plus 1. That is 1 upon. Cot square theta plus 1 gives you cosecant square theta, as we have done in the identities in class 10. Root cosecant square theta gives us cosecant theta. So 1 upon cosecant theta in the next step will become sine theta. That was our purpose only, to make the sine inverse of sine as identity and to get the value of theta. Now before differentiating, we have to put theta back in our original variable x. So let's simplify from here. We had taken x is equal to cot square theta. If you take square root on both sides, we get root x is equal to cot theta, that is theta is equal to cot inverse root x. Before differentiation, we have to come back to our original variable because we have taken the help of substitution only to simplify the function. Now this is our y. Differentiating both sides with respect to x, we get dy by dx, derivative of y with respect to x, is equal to, I have to take the derivative of cot inverse theta. Supposingly, I am taking root x as theta. So, minus 1 upon 1 plus theta square is the derivative. So, in place of theta, I am working with root x now. So, it is minus 1 upon 1 plus root x square into derivative of root x by chain rule, which is 1 by 2 root x. So, when we simplify it, it is minus 1 divided by 2 times root x into 1 plus x. So that is the derivative of y, that is derivative of sine inverse 1 by root x plus 1 with respect to x. Now let's take up third question. If y is equal to tan inverse x, find d square y by dx square. Second order derivative of y with respect to x in terms of y alone. So we want the whole answer in terms of y. Let's start with the solution. Y is equal to tan inverse x Applying tan on both sides, we get tan y is equal to x. So, differentiating with respect to x, secant square y into dy by dx by chain rule is equal to derivative of x with respect to x, that is 1. So this gives us the value of dy by dx as 1 by secant square y. And if I simplify this 1 by secant square y, it is cos square y. So we get dy by dx as cos square y. But this is the value of first derivative only, and we have to move to second derivative. So differentiating again with respect to x on both sides, LHS becomes d square y by dx square, second order derivative, and RHS cos square y, power comes in front, reduces by 1, then the derivative of cos y, that is minus sin y, then the derivative of y with respect to x. This is whole by chain rule. Power 2 comes in front, reduces by 1, basic function is cos, derivative is minus sin of y into derivative of y. So it becomes minus as such 2 sin y cos y into dy by dx. dy by dx is already solved as cos square y. So this can be written as minus 2 times cos cube y into sin y. And you can see the whole second derivative in terms of y. If you want, you can use this formula of minus 2 sin theta cos theta as minus sin 2 theta also. It's up to you. Another question, fourth question. If x square plus y square is equal to t minus 1 by t and x raised to power 4 plus y raised to power 4 is equal to t square plus 1 by t square. These two values have been given to us. Then we have to prove that derivative of y with respect to x is equal to 1 upon x cube y. Let's start with the proof. I start with the given expression only. This is given to us. X square plus y square is equal to t minus 1 by t. Squaring both sides. When we do the squaring both sides, it's always the whole square. Take care, you have to take the whole square on both sides. So on LHS, I am ready with the formula a plus b whole square. That becomes a square plus b square plus 2ab. And on RHS, we are ready with the formula a minus b whole square. That is a square plus b square minus 2ab. So accordingly you have to use the formula. Let's simplify. X raised to power 4 plus y raised to power 4 plus 2x square y square is equal to t square plus 1 by t square minus this t into t, 1 by t cancels and we are left with 2. Now look into this carefully. T square plus 1 by t square. This value is given to us as x raised to power 4 plus y raised to power 4 in the question. So I am going to substitute it. This is x raised to power 4 plus y raised to power 4 as given, t square plus 1 by t square. So this cancels and we are left with 2x square y square is equal to minus 2. Even 2 cancels and we are having a very simple function of y square as minus 1 by x square, which can further be written as minus of x raised to power minus 2. Therefore, y square is minus of x raised to power minus 2. Now differentiating both sides with respect to x, I get 2y into dy by dx. Y square derivative, power comes in front, reduces by 1 and then by chain rule derivative of y is equal to minus. It's also power comes in front, reduces by 1. When reduces by 1, it is minus 2 minus 1 becomes minus 3. So this is equal to 2y dy by dx is equal to minus minus is plus 2 and this x raised to power minus 3. Exponent is negative, so we can shift the term in the denominator. 2 also cancels. So dy by dx is equal to 1 upon. This y is in LHS in multiplication. So it goes in division. So dy by dx is coming out to be 1 by x cube y as we wanted, hence proved. With question number 5, find the derivative of root x into x plus 4 raised to power 3 by 2 divided by 4x minus 3 whole raised to power 4 by 3 with respect to x. First of all, we will start with the labeling of the function. Let y is equal to root x into x plus 4 raised to power 3 by 2 whole divided by 4x minus 3 raised to power 4 by 3. If I try to differentiate it directly, it would be too long a process by quotient rule and then by chain rule. So let's take log on both sides. That will really ease out the process of differentiation. So taking log on both sides, LHS becomes log y and RHS becomes, when I apply a log on this whole fraction, log m by log n will become log m minus log n, and in the numerator we have got the product. Whenever we take log or we apply log on multiplication, it becomes log m plus log n. So it would be something like this: log of root x plus 3 by 2 log of x plus 4. I have applied the property log m raised to power n is n log m minus 4 by 3 of log 4x minus 3. So this is how we can use all the properties of log. Log m into n is log m plus log n. Log m raised to power n is n log m. And log m upon n is log m minus log n. So let's start with the differentiation now. I have started with the process of differentiation. So derivative is 1 by y into dy by dx. Log of root x, its derivative is log derivative 1 by root x into derivative of 1 root x is 1 by 2 root x plus 3 by 2 is a constant, remains as such. Derivative of log x plus 4 is 1 upon x plus 4 minus 4 by 3 is a constant. Derivative of log 4x minus 3 is 1 by 4x minus 3 into derivative of the internal function 4x minus 3 is 4 by chain rule. Now this dy by dx is equal to, this y is in division over here, goes to right side in the multiplication. So y into this whole factor. I will be simply putting down the y value as given in the very first step. So that will save our time. I have put down the value of y that is going to be multiplied with the whole factor inside. Now let's simplify this. 1 by 2 root x into root x is x plus 3 by 2 into x plus 4 minus 4 4s are 16 by 3 times 4x minus 3. So this is the derivative. You can see derivative is a big expression, but we have really eased out our process of differentiation by taking log on both sides. Let's take up another question. Question number 6. If x raised to power m, y raised to power n is equal to x plus y whole raised to power m plus n, then prove that dy by dx is equal to y by x. So let's start with the given expression. You can see it is a sort of an implicit function where y cannot be explicitly expressed in terms of x. So they are so well connected. So let's start taking log on both sides to ease out the function. So it is m log x plus n log y is equal to m plus n into log x plus y. I have again used the properties of log. Log m into n is log m plus log n. So multiplication opens up into addition. And another property, log x raised to power m is m log x. So power comes in front. So that has been applied throughout. Now let's start with the process of differentiation on both sides. M into derivative of log x is 1 by x plus n into derivative of log y is 1 by y into derivative of y with respect to x by chain rule. Similarly on RHS, m plus n is a constant, derivative of log x plus y is 1 upon x plus y into derivative of internal function x plus y, that is 1 plus dy by dx. Let's simplify. So we are just simplifying it in this step so that it is easy for us to solve for. M plus n into 1 upon x plus y becomes m plus n upon x plus y into 1. So the term remains as such. The whole term is to be multiplied with the next term also. So it becomes like this. Now I am going to collect the terms of dy by dx on one side. So that would be n upon y minus m plus n upon x plus y, and the remaining terms on another side. So that is always there. This has to be shifted. When I take the LCM, it becomes y into x plus y. Let's cross multiply it, or you can say simply take the LCM. Nx plus ny minus my minus ny. You can see ny gets cancelled. On this side also we can take the LCM, x plus y into x. So it becomes mx plus nx minus mx minus my. Mx also cancels down. And if you look carefully, the common denominator x plus y also cancels out. So in the next step, we are having dy by dx into nx minus my whole divided by y is equal to nx minus my upon x. Again, this whole factor cancels out, nx minus my on both sides. So we are left with dy by dx is equal to y by x. This is only what we wanted to prove, so hence proved. Now the another question is, differentiate tan inverse 1 plus 2x whole divided by 1 minus 2x with respect to under the root 1 plus 4x square. So it is not the differentiating with respect to x. So it is differentiation of one function with respect to another function. I'll start with the labeling of first function as u and the labeling of second function as v. So you can see this is v. So now we have to solve for du by dv. Let's start with this function. U is equal to tan inverse 1 plus 2x upon 1 minus 2x. If you look carefully, it is nothing else but tan inverse 1 plus tan inverse 2x. With the help of the identity we have done in chapter 2, inverse trigonometric functions. It is a very simple function now which can be differentiated with respect to x because the variable is going as x. So du by dx is equal to tan inverse 1 is a constant, derivative is 0 plus tan inverse theta, derivative is 1 upon 1 plus theta square. In place of theta, we are working with 2x. So it is 1 upon 1 plus 2x whole square into derivative of 2x, that is 2. So when we simplify du by dx, it comes out to be 2 divided by 1 plus 4x square. Let's come to this side. V is equal to under root 1 plus 4x square. Derivative is very simple, as we do the derivative of root x as 1 by 2 root x. In place of x, we are having the whole term into derivative of the internal function 1 plus 1 is a constant, derivative is 0, no need to add, and the derivative of 4x square is 8x. This 2 cancels with this and we are having the value of dv by dx. Now required is du by dv. This we want, derivative of u with respect to v. This can be given as du by dx whole divided by dv by dx. So it is 2 upon 1 plus 4x square, and if I have to divide by this term, I can multiply with its reciprocal. Simply to simplify it, I have multiplied with the reciprocal. So you can see the term is same, having the under root. So half power is there, one full power is here. When we cancel it, it will be half power in the denominator. So we are having the answer something like this. 1 upon 2x into 1 plus 4x square whole under the root. So these were only a few questions of differentiation, and differentiation is a very deep, very vast topic. Keep on doing practice because differentiation will become your base for the next of the chapters, applications of derivatives as well as the integration. So keep on doing practice for such good questions.